Okay, so welcome. Let me just remind you where we stand. We had this question: when can we express, or when can we express or know that the category of modules over some algebra in monoid category is a module category over that, and then the other way around. And in the case of Grothendieck-Verdier categories, one result was that assuming we have equalizers, then just like for ordinary monoidal categories, the category of A modules, the right A modules, the left, not just module category, but GV module category. Remember, there was some extra condition. And then for the other direction, things are more complicated. I already mentioned that we need the concept of a generator, the generator of a module category M. This is an object in M such that M0, say, such that for any other object there exists an object in C together with an epimorphism from C acting on M0, this specific object, to M. And there is an analogous notion of co-generator where arrows are reversed. Now, there's a second new concept that we need, and this is the notion of M. So M is now always a Grothendieck-Verdier module category over a Grothendieck-Verdier category. We say that M in M is BIMSA admissible if and only if the bimodule functor internal HOM M to something. This is by definition a Lux module functor for the ordinary action of C is in fact a strong such module functor, and in addition has a Rayleigh join. Then there is, as usual, a dual, a corresponding notion. We say that it will be, maybe I write it again. That is block admissible, so this is this other tensor product. If and only if, not surprisingly, the internal cohom. And something is a strong, for the other action module functor. And this functor is by construction oblux, and we require that it's strong, and it admits the left adjoint. Once we have this, we say that M and add is the full subcategory of M on the corresponding admissible objects. And analogously, M block. Here we have just the other objects. And then in particular, in the case that we have the regular bimodule category C as a bimodule of itself, we will use the notation C hat and so on C hat block. Note, these subcategories can be small, they can be even very small, and they can be zero. It just can happen that the module category doesn't have any such objects. So that one should keep in mind. Anyhow, that one can make some statements. First of all, in the case of the regular binary category, where we have these subcategories. These are actually monoidal subcategories. And if I take any M, then M has a tensor is naturally C hat tensor module category. No, no, I'm not sure. I have to check that. Whether there's a hat here or not, it should be. Not in my notes. And then the analogous thing when we put the other tensor products. And now, once we have this concept, we can formulate a first result. Assume that C is a GB category, which is in addition finite abelian. And M a finite abelian GB module category. Then we have the following: the internal ROM appearing in the definition. So this goes from and I use the following abbreviation. We take the internal M for some object in the module category. I will reveal this by AM and analogously for the internal column CM. Then if I take now anything here, this will give me a functor from M to the category of AM modules that we have seen before. And the statement is then that this is an equivalence if and only if M is not an arbitrary object in the module category, but is in this subtransmissible object, and is the C generator. And analogously, the internal column, which goes to co-mod over CM, is an equivalence. I put it right here explicitly of C and then a tensor module category. And in the case of the internal column, we have instead the other tensor product. And then we need that M is admissible in the other sense, and it's a quotient. Now, by rewriting things and including a bit more information, one can then formulate the following result. Final result for this part. So first of all, assume that M is PV module over GV category C. Then we have that M is equivalent as a GV module to a category of right modules for some object, some algebra in C. If and only if the category M had a tensor contains a C generator and generator. And analogously, there is a statement with cogenerators. Don't write that down. And then in the case that C and M are in addition abelian, one has that the objects M such that the module category E is equivalent as a maybe I write it out as C center module. I use the same notation as over there. Are precisely the C generators in M. So not only in one direction. No, it's essentially already there. And then analogous statement for cogenerators and the other admissibility condition. This is still at the end of chapter 8. Now we will talk about relative Serre functors. Remember, we have introduced them. That was in 8.13. So I write it in a bit more generality. Let's assume that C is a monoidal category. M is a C module. And then D, a functor from C to C up, which I call duality functor. It would be a rigid duality or only Bergier duality, or maybe something else. And H, some functor from an opposite times amplitude. Then we say that relative Serre functor for M relative to H is a functor, call it S, from an angular functor of M, such that there is isomorphisms of H, therefore with respect to H, of any M prime, and then S of M, to E duality functor of H of M S prime. Makes sense? Okay. Morally, this means that we realize this duality functor by angular functor of M. And for what we are doing now, actually we need still a generalization of that. Say a partially defined relative Serre functor is a functor where we start not from M, but take some subcategory. Of M. And now in our case, and then we of course will require that, of course, for n prime in n hat and let me see, no, the other way around. Instance here. Okay, and in our situation, that's why I use this notation. The M hat will be either M hat tensor or M blob, as they just define it here, and D that will be the Courtois-Verdier duality functor T, and H will be the internal form. Now there's the following result. I have a statement. First of all, M is admissible if and only if there exists some object, call it S, of M in M, such that the internal Hom and internal co-Hom are related via the duality, via this S. So internal co-Hom S of M. And one is allowed to choose this S of M as, let's write it, the internal Hom. Let me do a mistake here. I take the right adjoint of this functor and apply it to K. So the right adjoint is the functor from C to M. So if I apply to K, that's the dualizing object in C, I will get an object in M. And then there are analogs for the other possibilities. So if you have instead the block here, then there has to be, I call it S tilde of M, such that the co-Hom, internal co-Hom, is isomorphic to the internal Hom, with the S tilde here, and important omission as module functors with respect to the first action of C. And in the other case, it will be with respect to the other action. And also then for S tilde, you can take the co-Hom. And then the left adjoint, and instead of the dualizing object, we take the dualizing object for the dual or the Verdier category, which is the tensor. And then we can show, first of all, the assignments S and S tilde obtained in this way extend to functors. which I still call S and S filter, from corresponding subcategories to M. And these are partially defined relative functors in this sense. And finally, we have an equivalence between these two subcategories. Which is given by, well, a slightly obvious notation by the restriction of the target category here to the other one. So it's part of the result that you always end up there, and then we use then the same notation. And that's the end of chapter 8. Now we start with something new.
So you have to show that the image of S
Yes.
is
Yes.
Okay.
But actually, this you do along the way. So you couldn't have an equivalence.
Yeah, of course.
Well, one should say, to be precise, the essential image. So up to isomorphisms. So this was the end of chapter 8. I do not continue to chapter 9 because I don't want to count beyond 9, and I will have chapter 9 next time. So I continue with chapter 6, which is background about categories. Now I look at variant or extension by categories. So this fits into chapter 6, first of all, because it is background for stuff that we want to do, but part of that stuff I will also include in this, and also to a little part, to a small part that I have treated already last year. But I will be much more detailed. So definition, the by category. B consists of the following data. First of all, the class, which we call the objects of B, or also the zero cells, or zero morphism sometimes, but I will typically say objects. And then for any pair, the A and B of objects, a category, which I denote by home with a script H, from A to B. This is called the home category sometimes, but I will not often use this. It has objects we call one morphism, or let me say one cells, shorter, and the morphisms we call two cells or two morphisms. And this includes, in particular, a composition of morphisms. This we call vertical composition. this is. In particular, since this is a composition of morphisms in a category, it will be associative. And then for any triple, the A, B, C objects, E, another composition, which we call composition functor. The categories. So this will have components C, A, B, C, which goes say from home BC and from B from AC. And I will denote this a bit strangely, but that's what I have decided to do. I have morphisms B and F here. They are sent to the composition. Remember, objects. So I call the objects here G, and the morphism say alpha. I will denote this by this composition sign, but then for the morphisms of the home categories, we cannot use the composition sign because this is already used here. So I write this as beta star. And I should say that this is actually one notation that is used somewhat frequently in the literature, but there are at least two other notations, probably quite a few more. So one has to be a bit careful, but anyhow, this is what it is. And then to complete this, there's an identity functor for any object A. Identity functor, which I given by I from 1 from A, where 1 here is the trivial category, which has one object and one morphism, namely the identity of that object. And then I will try to say not too much about this. There are natural isomorphisms. Which express associativity of this composition functor and unitarity involving this identity functor, and they correspond to two cells, which one denotes as H. With A with labels HDF, which is an isomorphism between these iterated compositions. And this looks like what we have for the associator of a tensor category or monoidal category. And this is not a coincidence. And analogously, there are analogs of the left and right uniter with components, say F. And of course, here F, G, and H should be composable one morphisms. And this will be one F after E, A, the F, and it will be after F. So the F for F monomorphism from A to B. And actually, these are the object parts of a more extended datum. we have pillars of the following form. If you look at the Cartesian product of 3 of these home categories, then we can use the C, B, C, D times the identity on A to get to hom D, B. No, hom, no, D. This was CD. Yeah, I leave it, I should write. So here I get to hom BD, this order, times A, hom AB, or I can do it, could say C, A, B, C, and the identity on B to get to hom CD times C, and then I don't write the names. These are then C, A, B, B, and C, A, C, B to get to hom AD. And this diagram will not commute, but it will commute up to an isomorphism which one calls A, B, C, D. And then one gets those A's here as when I look at objects here. And analogously, there is something for unitas. I don't draw that to save some time. And then there are axioms. All of this is still data. And there will be axioms, which not surprisingly, it looks like associator for a monoidal category. So there is a pentagon and two triangles analogous to the associator and unitas in a monoidal category. So let me just maybe indicate the pentagon. There's a rewriting of the pentagon for a monoidal category with different symbols. So we would have 4 homomorphisms: the K, H, G, and F, and we relate this iterated composition to the composition in totally opposite order, and we can do this in 2 ways. Either we first go here to K composed with H and compose this with G composed with F, and then from the definition it's clear what A we have here. Let me write here. And here, when we do this, this would be an A with labels K and H and GF. And analogously here, we can say AHG to change the order of bracketing the first bracket to get to K composed with H composed with G, and then composing with F. And analogously on this side, around here, we can go to K composed with H composed with G composed with F, and then use the change the ordering here, and similar triangle diagram. Now, why are bicategories of interest? Well, as usual, Did I give a number for this? This was 610.
You wrote 613.
613 is general subsection about bicategories.
Okay.
And the definition is 610. When it's these sections or not these topics, I put them in a some background. Box. Because there are important examples, they just appear in many situations. And let me mention one of them, which we have seen. Now, first of all, maybe it's a bicategory of categories where objects are small categories. One morphisms cells are functors, and two cells are natural transformations. And you need a restriction here to small categories in order that the one and two cells will be together form a home category. So the home AB is what we previously take to be. Another one which implicitly we have looked at is the category of K algebras. In this case, the objects are K algebras, where K is a field, say algebraically closed. So ordinary algebras, and then the home categories from A to prime are just the A prime modules. So the one cells are bimodules and the two cells are binodal morphisms. And then, an example, make relates to what we have seen for the associators. Assume that C is a monoidal category. Then we can there is a category called the D-looping of C, and denoted by DC sometimes, where there is one object, we call it star, and then there is correspondingly one home category, and this home category is just C. And then, of course, the composition is the tensor product. Composite functor is the tensor product. And in fact, one can show that any one object bicategory is of this type. Well, equivalent with bi-equivalence, a notion which we have not really defined, but it's clear what it is. So let me start. And then I have to continue after the break with some graphical description of some of these notions. Recall, in the case of categories, we can denote morphisms in this way, and then we can use a Poincaré duality to get the string diagrams. And analogously, we can do the same thing here. There is analog of this mapping notation is what one calls the pasting diagram. So if I have two objects A and B, then I can have one morphism between them. But if I have one morphisms, then I can have a two morphism between them, and one uses this notation. So here alpha is a two morphism from F and B. And then this notation, vertical composition, amounts to the following. So we have the alpha, the two morphism from F to G, and beta, the two morphism from G to H. Then vertical composition sends this to two morphism between F and G, which is beta composed with alpha. And the horizontal composition is as follows. We have the two morphism alpha between some S and S prime, which go from A to B, and then we have G and G prime, which go from B to B, and the morphism, two morphism beta between them. Then the horizontal composition corresponds to the diagram, where we directly go from the G composed with F to G prime composed with F prime, which are one morphisms from A to C, and then we have I call this alpha prime to make a distinction from beta here, and then we have alpha prime. And still a minute or two, let me mention a special case. Yes, which one sometimes conveniently can use. This is known as whispering. If we have the situation that we go from A to E and to C in a situation where we actually have the same one morphism here and the identity two morphism of H here, then we let's call this alpha here, and then we write this also as alpha, and then just H. So here we have a horizontal composition of the two morphisms and the one morphism back. And then there is, of course, one way you have the identity on the other side. And still, sometime there's a fructification result. Analogous to the one for monoid categories. Every bicategory is bi-equivalent to two category, where the two category is a bicategory where the associator and uniter are all identities. And bi-equivalent means via a functor between bicategories, which is equivalent, so that we need the notion of functor between bicategories, and then we will introduce after. Well, it's what one should expect. and I will take this up after the break then. Oh.
It's probably fine.
Not really according to this class.
What time do we?
At 25, and it's not yet.
Okay.
We can start. One further comment here. There is a relation called the interchange bound between the horizontal and vertical composition, which amounts to saying the following. Assume you have a vertical composition like that, and you have a vertical composition like that, and then you compose them horizontally. If you draw this picture, you could also say you have a horizontal composition here and a horizontal composition here, and you compose them vertically, and this gives the same result. So the picture is unambiguous. Coming back to the string diagram notation in the case of categories and then monoidal categories, we can do the analogous thing here via Poincaré duality. We will now have two morphism alpha from F to G. This looks like for categories, except that we got one step higher or lower in the meaning of the symbols. But then we have A and B, and these they have to associate to the two-dimensional regions here. And remember from the situation monoidal categories that we should think of such diagrams as embedded in some, say, rectangular canvas which actually is framed. So we have a distinction of these two directions. And this is now important because if we look at vertical composition, this corresponds to the situation that we have a morphism, a two morphism from F to G, like here, and then we have two morphism from called beta here, from G to H. All of these are morphisms involving A and B. So we will have this picture for the vertical composition. And maybe that's why we call it vertical. I should say, not yet. Vertical composition, remember, is strictly associative. So there is no problem with notation. If we do horizontal composition, we will have a situation where alpha is a two morphism from F to F prime, where in the regions we have A and B, and then we have another two morphism alpha prime, between G and G prime, and we have C here. And this is now interpreted as saying as we have alpha prime star alpha as a two-morphism from G composed with F, with G prime composed with F prime, where it will be A and C, and I do not will not really use the we'll have this equality, but remember this composition, I didn't say it explicitly, but it follows from the definition. It's not required to be associative, but only, no, I did say, I think, associative up to isomorphism. So this in general will not be strictly equal, but we have the strictification results where the associator is trivialized, and precisely like in the case of monoidal categories, we can use this string calculus once they say we go to a bi-equivalent strict bi-category, so a true category. And again, like in that case, essential information is not lost. We can reproduce things by, there's only one way to, if you write this in formulas, to insert the associator and then analogously doing this at the right place. Let me maybe just another picture. If you have a morphism, a one morphism, a two morphism alpha between composition up to one morphisms to some other one, which I call F, then the picture would be, say, if H goes from A to B and G goes from B to C, and then F will go from analogously more complicated pictures, and these pictures are convenient in helping with proofs, but actually I will not use them at all. I think I will next time use a similar graphing calculus, where, however, the canvas is not a rectangle, but we can be more relaxed. Then very briefly, when we have bi-categories, we have also analogous notions of functors and natural transformations. So the functor in bi-categories, F from B to B prime, is an assignment of F of A in an object in B prime to any object A in B. And then a functor F with labels A and B between the home categories in B, between A and B, and the home categories in B prime, between F of A and F of B, or any pair of objects. And then invertible two cells called phi A from the identity of F of A to F of the identity of A for any A, and phi G, F from F of G composed with F of F to F of G composed with F for any F and G which are composable one cells, and then there are axioms which I do not write down. They are coherence conditions which essentially say that this fits precisely with the structure of bicategory on B and B prime. And there is a book by Gersti where you find the details, but they are a bit lengthy. What I should say is that in the larger part of the literature, these functors between bicategories are not called functors, but pseudo functors. I don't particularly like the terminology, but I think one reason is you don't want to call them bifunctor, because bifunctors are sometimes also used for functors from a Cartesian product of categories to something. And then analogously, the next step will be a natural transformation. But in this case, I have no choice. I call it pseudo-natural transformation. So this will be alpha from F to G, where F are subfunctors or pseudo-functors between the same bicategories A and B. And this assigns a one morphism, let's say alpha A. No, I should use capital A. This goes from FA to GA for any A, for any object A. And then it assigns an invertible two morphism. I write this here. Invertible two morphism alpha F to any one morphism between object B in A such that this alpha F fills a square, and then we consider FA going F of F as A prime, say. Then we have our alpha A, which goes to G of A, and alpha A prime goes to G of A prime, and here we can go via G of F. And this diagram will not commute, but rather it will commute up to certain invertible two morphism. And then, of course, there are again axioms, which are covariance condition. For these, I recommend it. But that's not the end of the story. In the case of categories, the two-layer structure, and then we have three layers of structures, the category itself, functors, and natural transformations. Now we have one layer more, and accordingly, there is another notion which is called a modification. Call it M from alpha to beta, where alpha and beta are pseudo-natural transformations. Alpha beta from F to G, and F and G as before. And this assigns now a two morphism or two cell alpha M A goes from alpha A to beta A for any object A. And there are axioms which again I don't write down, which are lengthy. Just to show schematically what happens in the case of categories. We have functors in natural transformation. And we can look at the level of objects, and let me call them directly one cells, morphisms, or the functor associates an object to an object and the one cell to a one cell. Whereas a natural transformation assigns a one cell to an object. Whereas in the case now of bicategories, we also have two cells, and the picture simply continues. But then we also have modification. Where we assign to a 0 cell a 2 cell directly. There are no things to do. Then we will also need the notion of monoidal bicategory. And already here I have not written down a good deal of information, maybe the axioms. And in the case of monoidal bicategories, I will be even shorter. Otherwise, I could use the rest of the day for writing these things out in detail. But morally, it's not hard to understand what's going on. So in the monoidal bicategory, we have a bicategory together with pseudo-functor from the Cartesian product of B with itself to B, and can be we can call it a tensor product, pseudo-functor that is associative and unitary, not directly, but up to specified non-morphisms. Which again are called associators and unitars, and also denoted if we need it by alpha, UL, and UR. And then these are in turn not invertible as before, but invertible up to invertible zoomorphism. Just going from a categorical level to the bicategorical level, we just relax things as soon as we can say up to something at the next level. We say this, and analogously, you can go to higher categories and higher monoidal categories. But things become quite a bit more complicated. I can take a short comment in a minute. Now, in this case, also this statement applies to the pentagon. So the associator satisfies pentagon identity. But this is not an ordinary pentagon. which commutes as a diagram, and that a pentagon that commutes up to the filler, which is an invertible two-morphism, which is called the pentagonator. And here you find details in the PhD thesis, of course. Then once you have monoidal categories, there will be also monoidal pseudo-functors. And then you relax things. So this is just a functor between bicategories, which is compatible between bicategories which are both monoidal, and it's compatible with the monoidal structure. So in particular, one morphisms. F is the functor. It goes from F A over F of T to F of A tensor B, analogously as in monoidal category, and there is a one morphism from one in B prime, F of 1B, and now these are not isomorphisms, but they are invertible up to invertible two morphisms, which can have to satisfy certain conditions, which again I don't write down. Let me mention at this point, without writing, that the coherence result that we have for bicategories does not extend to higher categories. For the case of, for the next level, there is still a partial result, which says that any tri-category is tri-equivalent to a certain type of weak three categories, so not a one where everything are identities. And this is called a gray category, which can be described as a category enriched over the symmetric monoidal category of two categories and strict two functors, where the Cartesian product is modified to something called a gray product. And I don't want to say more about that, but just mention that a monoidal bicategory can be regarded via D-looping, well, the next level of D-looping, as a gray category with one object. Then once you have the notion of a monoidal bicategory, you have the notion of symmetric monoidal bicategory. Where one morally says that the tensor functor that your I should point here the tensor pseudo functor satisfies all possible conditions of being commutative up to equivalence, well, up to something higher, and then there's an analogous notion of symmetric monoidal functor in those. I should mention, I didn't introduce, because I don't need it, separately braided monoidal bicategory. You can define that. But it turns out that in the bicategorical sense, a situation between general braided and symmetric, there is still something in between where only part of these conditions are satisfied. These are called syleptic bicategories. And I don't know anything about them except the name. Now let me come back to the question I posed before. Why should we care about bicategories when I gave examples? But now let me say a bit more about them. Well, further motivations. One we actually have seen before. That was in 782, where we talked about, well, where we were looking at boundary conditions, topological boundary conditions for topological field series in 3 dimensions. And then we saw that they can be described with the help of monoidal module categories over a certain fusion category, which we get from a single boundary condition, and then we can look at all the boundary conditions, and these actually form the bicategory or bimodule categories. Well, in that case, everything is semi-simple. Let's add this here, but I don't. Over the monoidal category. Let me mention another application in what you might call physics. What you call a gauge theory in quantum field theory is roughly, no, I don't write anything, I say it in words, that you express certain locality properties of your theory with the help of some fields which are described by principal fiber bundles which, for some group G, which is called which is called a structure group, typically a compact Lie group. And these principal fiber bundles naturally form a category. But you can also look at situations where you do not have gauge transformations, which correspond to doing something in these fiber bundles, but you can also have gauge transformations of gauge transformations, and actually discontinuous. But if we continue one step, then there is again a geometric description of that via what is called bundle chirps, and bundle chirps naturally form a bicategory. And then another one is modular functors, or also topological field series. And I will say more about this after the next comment in connection with what we have here. It is 121a, because this is a result due to taking of Nietzsche prostrate in Lüger. It says that if A and B are fusion categories, and I apologize for using the same font now for categories as I did for by categories. I could use a different font for by categories, but I want to reserve another font for double category translate. So, in this case, the Grünfeld center of A is equivalent as a braided category to the Grünfeld center of B if and only if A mod and B mod introduce notation here are equivalent as by category. And this actually, in this application here is important because it tells you that the description we had is take some boundary condition and then you get all via this bimodule this by category, but you could start from just any other one. And remember, we had to do with central functions there, and then this precisely guarantees you that the description, that the end result is independent of the boundary condition you start with. So now to this motivation here. For this I will need some time to give some details. So this is now about maybe I should write extended model topological field series, but I will say not much about them in modular functors. And if you look in part 735, I have given you the definition of a topological field theory as a symmetric monoid functor. I'll just from some category of, say, oriented cobordisms to vector spaces. And this we could do in any dimension. D, actually for concreteness, talk about three-dimensional topological field theory. Then this is the category when objects are two manifolds, closed two manifolds, and all the manifolds are smooth, compact. So I will not say this each time. And then the morphisms are three manifolds, which are interpreted as bordisms or cobordisms, which have two parts of boundary of their boundary, one incoming, one outgoing, and correspondingly. And they have a symmetric monoid structure given by this joint union. Vector spaces have the and now what the composition that we have here is gluing, and in a quantum field theory perspective, one could say that the gluing realizes also an aspect of locality in the following sense. If we look at an arbitrary cobordism, we can chop it into pieces of a simpler form. Say in the corresponding case where we have 2, 1, we will have actually objects will just be disjoint unions of circles. And we would have the identity morphism. We could have something like this, which is called a pair of pans. And then there is the opposite, which is sometimes called a pair of copans. And we have a cap and a cuff. And by chopping these into pieces, we can reduce everything to those 5 possibilities. And analogously in higher dimensions, it becomes combinatorially more complicated. But in any case, we get to a small set, relatively small set of elementary cobordisms. And we only, if we understand those, we understand everything, provided we know what happens when we chop somewhere. More local information. But now when you do that, you can say, well, we could also, in higher dimensions, we could chop 3 manifolds along 2 manifolds. We can also chop these 2 manifolds further, like here. And then we get to the notion of extended locality. When we get an analog solution of extended topological field theory, which is now in the simplest version. Again, you in higher dimensions, you can go still higher. It will be a 2 functor, just a 2 functor. I don't want to say pseudo functor all the time. From 3 to 1 cobordisms, which are now where the objects are 1 manifolds. Again, like here, the 1 morphisms are 2 manifolds, like here, and then the 2 morphisms are 3 manifolds. Obviously, 2. Now, another thing to do is 2 vector spaces, except that there are several concepts of 2 vector spaces. The one I would use here, but I will not use it directly. Say for words is that the objects here are k-linear, finitely semi-simple categories. So this is a rather restricted definition, and the 1 morphisms are functors, and the 2 morphisms are natural transformations. We can also actually try to go further to extend this to the point. For a typical topological field theory, we cannot do it. For example, the Torayev construction that I mentioned can be extended to such a thing, but it cannot be extended to the point, 0-dimensional, that if the underlying modular tensor category is a fringe delta. And things become more complicated, and I will more modest look at what people have called the modular functor. This would be roughly the 2,1 part of 3 to 1 extended topological field theory. And I will write this down in detail, but actually it turns out when you do that, it is natural to generalize from functors as 1 morphisms in the target by category to pro functors. I will say a bit more about that. But let me remind you that we have talked about row functors briefly before, but I haven't written down the number now. So, what do we need? We need to describe this category. Actually, we also generalize this because this is needed in applications. We allow for physical boundaries in the same sense as we encountered when I talked about the conformal field theories. And then I guess so this is 1, 2, 3 has 3 parts. Part A, where we look at the bi-category cobordisms oriented in 2 dimensions, and I call them open close. So this is going down 1 dimension, which are sometimes called 2-dimensional open closed cobordisms. This is somehow a misnomer coming from conformal field theory. You allow for 1 manifolds which are closed and 1 manifolds which may have a boundary, and you call them open. And this is the following bi-category. So we first have to say what are the 0 cells. Let's call them alpha. This is previously this would be a finite disjoint union of circles as 1, but now we allow also for 1 manifold with boundaries, and then we also have intervals I, where actually we think of S1 really as the standard circle, which means the unit circle in the complex plane. And as the interval, as the interval from 0 to 1. And also with some choice of orientation, I will suppress anything about orientations. And then we will have to deal with embeddings of the standard circle and interval into subsets of the boundary of a 2 manifold. And then the 1 cells, I will denote by sigma from alpha to alpha prime, which are compact, oriented, smooth. Surfaces of 2 manifolds with boundary. Together with, it's more important, the map I call the parametrization of the subset of the boundary. Important in general, really a non-trivial subset. Call this phi. Consists of 2 maps, phi plus and phi minus. Yeah. Last. So if sigma goes from alpha to alpha prime, this goes from alpha prime to d sigma, an orientation preserving embedding. Phi minus goes from alpha to d sigma and this orientation reversing. And then the two involved subsets of the boundary should be disjoint. One cells, then we need two cells. Sigma to sigma prime. And these are now isotropy classes of these homomorphisms from sigma to sigma prime, compatible with the parametrization of the boundary. So we require that phi plus minus for sigma prime is the same as composing phi plus minus for sigma. And then we need composition of one cells. This is gluing. So I have a one cell sigma from alpha to alpha prime, and then sigma prime from alpha prime to alpha double prime. We glue along alpha prime. Actually, since we require our surface to be smooth, you do not glue along such a circle or interval, but along the color, including that. And you have to be a bit careful because you have to make choices. And actually, the choices are not canonical, but it is known that you can deal with that. And then, oh, I missed it over. Let me just complete this. And then there is a vertical composition of two cells, which is just induced by the composition of these homomorphisms. You take representatives and compose them, and then take the isotropy class, and then horizontal composition. It's again gluing. And finally, the tensor product as before is joint union. With tensor unit, the empty set regarded as a 2 or 3 minutes. Okay, so that's part A, and then part B will be the bi-category of profontes. bicategory of open-closed covariations. Then we have the bicategory denoted by growth K. In the middle is the one of K linear. K is usually that's algebraically closed. K linear profunctors. Maybe you remember what a profunctor was, but if not, we repeat it here. In this case, the objects are more or less like what we had in the case in this description of 3-to-1 extended topological field series, except that to go to the full topological field theory, there is always some need of a certain semi-simplicity assumptions, and that we do not need here. We say then object is just a K-linear finite abelian category. And then the one cells, well, they are functors, but first of all, since we typically do not require semi-simplicity, we will not take all functors, but no, only left exact functors, but not functors. Say if we call the categories A, not functors from A to A prime, but rather functors, say F, from A opposite times A prime to vector spaces. And as I mentioned, when I introduced profunctors in the literature, very often the role of A and A prime is interchanged. So one has to be a bit careful. And in order no, let me keep it like that. And then two cells are, so say from F to F prime are natural transformations of such functors. If you want, I will not need it now, but a bit later, or maybe next time, if we want to make sure that we do not mix up functors from A to A prime with functors that are relevant here, which we call profunctors, sometimes one puts a little sign here. And then we have to tell what is composition. Of one cell. So if we have functors, we can directly compose them as maps. That we cannot do now. What do we need? Well, we have a functor taking two arguments. Or the second x. We have another functor. This should be f prime. Another functor from where we take x here, and that is something arbitrary. Here's a different sign. And as I did partly before, when I think of an object in A as an object in the opposite category, we could use the same symbol. It's unambiguous, but to remind us that it's in the opposite category, I put a bar on it. We take the K linear tensor product, and then we take the co-n over all x in A prime, such that, and then this we define as the composition F with F prime. And the vertical and horizontal composition of two cells, where two cells are just natural transformations, so we just compose them as natural transformation. And I think this year in the recap at the beginning, I didn't really write out what these are, but I think I did it last year. And anyhow, we find this appendix. Now part C, definition. Open closed modular functor. I do not like this terminology open closed, but I have to use it because everyone else does. Is defined to be these are symmetric. Yeah. Also, it's rather clear what the symmetric monoidal structure here is. So this is a symmetric monoidal functor between bicategories. Let me write it out in pseudo functor. For reasons that will become clearer next time, I call it BL from between these two bicategories that I have described. Next time I will talk about what is called string nets, and string nets in particular will provide us with such a symmetric monoidal pseudo functor. I should mention here that the terminology modular functor and also open closed modular functor is not used for exactly the same thing everywhere in the literature. So there are various types of constructions which then are all regarded as instances of such a modular functor. But it's not always clear whether the definitions are equivalent or not, and there has been some disputes even in the past about whether what one person was doing was equivalent to what someone else was doing or not. But I will give a concrete construction, and this is then what I will and precisely I will use this definition of open-closed modular functor. Now we get to something else. I still continue in chapter 6 because I introduced bicategories in them, but this is now completely new compared to, or also this part was new compared to last year. And this is about pivotal bicategories. Pivotal definition. Do not start with bicategories directly, but we say that there is a Morita context or categorical Morita context, or the two Morita contexts. This consists of the following data. There are two finite tensor categories. Of course, you could generalize this to other situations, but then not everything will automatically work. Well, you could definitely extend it to multi-tensor categories, but I have not talked really about them, so I don't allow this here. Let's call them A and B. And then two bimodule categories, which I call M and N, and M is the AB bimodule and N is the BA bimodule. And then two bimodule functors, which go from M tensor over B with N to A, and from N tensor over A N to B, and then we call this, well, this is not a theta, it's a encircled minus and a box minus, and just these were introduced in order to distinguish them from other symbols that were also used. So in itself, they don't say much. I have to tell you, well, and this is really, well, S bimodule. So here I have an AB bimodule and a BA bimodule. A here is the regular bimodule. So this is a functor, bimodule functor between AA bimodules and analogously here BB. And here I have what is called the relative the linear product. And I don't want to give details about that, but it's analogous to one categorical level from lower, just tensor product over A or over a ring. So remember, this was defined. Well, you could define it by a co-equalizer, but you can also define it by a universal property. And analogously, one defines this by a universal property. And let me just mention that it follows, for example, that if M is a category of late A modules and N is a category of right B modules, and I need only modules here, so left, right and left. Let me see, N. So if I take the relative tensor product over A, then where A and B, let me say in some monoid category C, then M relative the linear tensor product C N is equivalent to A binomial. And then, in addition, you need two bimodule natural transformations, which are isomorphisms. I will start from alpha and beta, which are fillers of pentagons. I draw one of them, and see what the other one looks like. So we can look at M tensor over AN, and then tensor over B of M, which is easily seen to be equivalent to what we get if we change the bracketing. I do it, no, I did it. And this should be B, and this should be A. I can use the first functor, yes, to go to A tensor over A M, and we actually use the other one to go to M tensor over B B, and of course A is the tensor unit for the relative tensor product, and so by doing things again, I just get, no, sorry, by these are now left and right modules, so I can use the action functors to go to M, and then this the alpha would be such that the diagram commutes up to alpha, and analogously for beta, where you exchange the roles of M and N and A and B. And then, of course, these are the data. There are axioms, which are again in the form of pentagons, but I will not have time to say anything about them. Then